So, this week we're going to see heat transport. So, the idea is that we're going to see some transport equations in general, not just for heat, because it's all the same math, so it makes sense to put them all together. We'll define the mean free path. Okay, so back to kinetic theory of gases, if you want, looking at the microscopic pictures and define what's the mean free path. And then describe diffusion, heat conduction, and viscosity, which are three pretty different, physical mechanisms. But in the end, they all, in a fluid, they all come from the same type of phenomena, and they have almost the same equations that describe that. And then we're going to get into the black body radiation. So pretty much it stops here for your studying the mid-semester. Black body radiation quickly, and use heat transport, both conduction and black body radiation, to explain how heat is transferred in simple systems. Okay, because up to now we've seen the idea is that we've seen thermodynamics in different ways. We've defined entropy last time, first law, second law. Now we need to think a little more about if heat is so important, if it has to be transferred from one object to the other, then it makes sense to actually start looking into how is this right? How is this transferred, this thermal energy? So that's what we're going to do today. So transport processes in general. Okay, so the general idea for transport processes. So the general concept is that there's always some type of equation that will tell you how some quantity changes as function of time, and this is going to be equal to some coefficient that we can call a transport coefficient. It just says how efficient this transport is, times the area through which the transport is being done, times typically minus the gradient of a quantity. Okay, that's the general idea. So you have, in the case of heat, for instance, you have a temperature gradient. So it's warmer here, it's colder there, and then you want to know how much energy, how much heat is going to be transferred as a function of time through a given area in between these two extremes. And then, of course, if you double the area, normally you would have twice as much heat going through, right? So that's why it's proportional to the area. This transport coefficient is just something that tells you how efficiently heat is being transferred. And then the gradient is how strong is this change in temperature. You expect that as you increase the difference in temperature for a given distance, as you increase the gradient, the heat transferred is also going to increase in a linear fashion. Okay, so that's the linear version. As soon as you get into very strong, for instance, if the gradient becomes really, really large, or there's something else happening, then you get into a non-linear regime, and we're absolutely not going into this. I mean, this is fine for many applications. So equations that actually follow this recipe are, well, there's heat, and then that's called thermal conduction. And then the equation in this case is going to be dq dt is equal to minus kappa, so that's the constant, that's this transport coefficient, times the area times the gradient of temperature in x direction. Okay. In the case of if instead it's matter that's being transferred, okay, then we're talking about diffusion. And in this case, it's the number of particles that go through a given area as a function of time. And there's a minus, and there's this transport coefficient, and this time is called the diffusivity. And then there's the area again, and then there's a gradient in the density. Okay? So if there's a higher density of particles in one side and lower density of particles, then you expect that there's going to be, you know, a rush towards equilibrium, and the particles are going to slowly diffuse in the direction where their density is lower, right? And that's why there's this minus. Sorry. This here, that's the number density, the gradient in the number density. Yeah. So, temperature gradient. And here it's number density. Gradient. And then finally, there's another case where we can actually transfer momentum. Okay? And in this case, what we're talking about is viscosity. And in the case of viscosity, there's a transfer of momentum, for instance, in the x direction as a function of time. And it's equal to minus, this time it's the Greek letter eta that we use, that's the viscosity, and area. And then there's a gradient, but the gradient has to be in an orthogonal direction. So now we have to use. So it's the case where you have to imagine that you have a fluid, and then there's a part of the fluid that's going at some speed, and the other part that's going, say, it's not moving. Okay. So there's going to be a transfer of this momentum. You know, this part of the fluid, if it's moving that way, it's going to transfer, and then this part of the fluid is slowly going to start to accelerate also. So there's going to be this momentum that's being transferred through the gradient. Okay, and viscosity tells you how efficiently this transfer is being done. Okay. Okay, so those are the three, main. So that's how is it called? It's the velocity. Something like velocity shear. I don't remember the exact technical name, so I'll leave it free and I'll look it up and fill it later. Okay, so we're actually viscosity is something we're going to barely touch upon. So we're going to focus more on heat transport. So heat transport typically can be done through three different channels. There's the direct conduction, okay, that we're going to look at now. There's radiation, which is blackbody radiation. We're going to look at a bit later. And then there's what's called convection, which is a way to transmit heat by bringing large amounts of materials, or kind of collective motion of material at different temperatures. And it turns out that this one is quite messy. It's difficult to characterize it and to model it. It's fluid mechanics. There's lots of complicated math associated with it. So we're not going to look at convection at all in this case. Convection in some cases is quite important. In some cases it's negligible. But yeah, we're not going to look at convection much. So let's look at heat conduction in more detail. So what you have is you have to model your material as some kind of cube like this. Sorry, my perspective is a bit like this. And then there's an area A through which the heat is going, and there's a distance x like this. Temperature, you say temperature T, and here is going to be T plus delta T. So already we're out of equilibrium, of course, right? Because now we have a single material that has different temperature at different places. Okay, but locally you can still assume that there's some kind of equilibrium. If you look at a small enough volume, then the temperature is well defined. Right? So the idea is, in this case, you would say the heat transferred per unit time is this, minus kappa A times delta T over delta X. Okay, or I can write it again the way I wrote it before, like this.
And by the way, this is called Fourier's laws. Fourier's law. Okay. Kappa is called the thermal conductivity. So sometimes you're going to see another version of this law where Q dot, so dq dt, you're used to this dot notation, right, for a time derivative? Yes? Okay. Q dot is divided by the area, and then you define this as a flux. Okay, so a flux is an amount of quantity per unit time per unit area. And then what you get is that you can define the flux, for instance, in the x direction, which is minus kappa times gradient in x. And then what's nice is that you can write it in 3 dimensions. You can say that the flux is actually a vector, and it's minus kappa times the gradient in t in 3 dimensions. Okay, so this is equivalent. Have you done multivariate calculus? This type of gradient, 3D gradient, you've seen that already? No. Okay. Some of you yes, some of you no, I guess.
We're going to cover it in the next couple of weeks.
Ah, okay. So that's what at some point he's going to. Yeah.
Okay, so it's just a way to put 3 derivatives in a vector in this case. Okay.
We've done this before in the main module, but semester was briefly.
Ah, yeah. Okay. I guess in electromagnetism, I mean, you kind of need this, right? Yeah. Okay.
Relating electric field and voltage.
Yeah, exactly. Yes. Yes. Okay. So yeah, that's that's a grown-up version, if you want, of this equation. Yeah.
What are the units of kappa? So it's joules per
You know how to compute how to figure out the units? Yes. Right. So you could look at Fourier's law, for instance, and you would say, okay, from one side it's joules per second, and on the other side it's square meters times Kelvin per meter. So then it's just going to be just meters times Kelvin, and then you have to divide by this. So joules per Kelvin second meters. Right?
Or you could say watts per Kelvin meter. Or sometimes of course it's watts per meters degrees Celsius.
Okay, so typically when you're going to look up in a table, if you want to know what is the thermal conductivity of some material, it's going to be given in watts per Kelvin meters or watt per Celsius meter. I think it kind of makes sense, right? You know, watts is the amount of heat, the amount of energy per second, and then if you multiply it by some distance, the overall efficiency is going to be lower. The gradient, kind of decreases if you stretch the extent of your system. Okay, should we do right away an example of how to apply this equation? We're going to do it on heat conduction through a single glazing window. So we set this up by just putting, we have a model of a window. We're going to say that it's 5 millimeters across, and that on one side it's 0 degrees Celsius, which is quite realistic by now, 20 degrees Celsius on the other side, and we're going to assume that the window is 1 meter by 1 meter, okay? So the question is very simple. how much heat is going through this window per unit of per unit time. So we're going to find something in the end that's in watts, right? So, anybody wants to tell me? It's relatively simple. How would you do it? You just write down Fourier's law first.
You know that it's going to be useful, right? So Q dot is equal to minus kappa A dt dx. Oh, I should tell you that kappa for glass, you need this also, is 0.8 watts per meters per Kelvin.
Okay. Do you see that it's really just a matter of plugging numbers? Mm-hmm. Yeah. Right? Kappa we know, put it there. Area is 1 meter by 1 meter. And then gradient is 20 Kelvin divided by 5 millimeters. Yeah?
So, sorry, I'll just put this somewhere else. We can just plug in the numbers. Minus 0.8 watts meter minus 1 Kelvin minus 1 times 1 meter squared times 20 Kelvin divided by 0.0005 5 meters. And if you put all these numbers together, you're going to get 3.2 kilowatts. Okay.
So that's a lot of heat going through a window. I don't know if you guys are unlucky enough to have single glazing windows in your dorm. In reality, it's not that bad because there's actually a layer of air on both sides that acts as a much better isolation than the glass itself. So if it's windy and if there's lots of air currents, then this effect actually is much lower, and that's the part about convection, right? But if air is still and kind of trapped on both sides, this is a really an overestimate of how much heat is going through this window. Yeah.
Don't you need to convert the 20 degrees C to Kelvin?
Yeah, whenever you have a difference in temperature, Celsius and Kelvin are the same, right? So you have to be careful, but as soon as you have a delta T, is the same.
Oh, it's just 20 minus 0.
Yeah, exactly. So you could say it's 293 minus 273 is still 20. Okay, so that was easy. Let's compute the case of a double glazing window. That's a little more involved, right?
So double glazing window. What do we have? We have two slabs of glass now. So one here, one there. Okay, and we're going to say that there's roughly 1 centimeter in between. Both are still 5 millimeters. And still 1 meter by 1 meter. And yeah, that's it. The only thing you need more now is that the thermal conductivity of air is 0.024 watts per meters per Kelvin. Much lower than glass, right? Which is not that surprising. So,
what should we do in this case?
Three sections?
Yeah, 3 sections. What do we know about there's going to be something that we have to, something that's conserved, some yeah.
Is the temperature gradient constant?
Is the temperature gradient constant according to you?
I would say so. I don't know.
I would say no. I would say that, probably the gradient, yeah, actually we can draw it.
Probably it's something like this. If you look from the side, temperature probably does something like this, and then like this, and then like this, right? And that's 0 degrees Celsius, and that's 20 degrees Celsius.
The total rate from one end to the other have to be the same.
I'm sorry?
The total rate from one end to the other have to be the same.
Yeah, exactly. So that's the trick. You have to think, okay, I don't know what's the temperature. Well, I know this temperature, I know this temperature, but I don't know this one and that one, right? So there's two intermediate temperatures that you don't know, and we'll have to figure it out in one way or the other. But one thing that we know is that whatever heat is coming here through, we're in a steady state, right? A steady state means things are changing, but they're changing in a constant way. Okay, so the heat that goes through is always the same. So you know that the amount of heat that goes through here per unit time is the same as the amount of heat that goes through here per unit time, which is the same that goes through here per unit time, which is the same, right? Otherwise, if it's not the case, then heat accumulates somewhere in there, right? And then there's a temperature change and this stuff. It doesn't make sense, right? Okay, so that's the trick. We're going to be able to say, to apply Fourier's law from there to there, and we're not going to be able to solve it yet because we don't know the temperature there. But we can apply it from there to there, and then we have a relation between these two temperatures, and we have it from there to there, and we have a relation between these two temperatures, and then we can shuffle things around, and we're going to be able to find a solution. Okay?
So, let's say that this is 1, 2, 3, and 4. Okay? So we know T1 is equal to 0 degrees Celsius, and T4 is equal to 20 degrees Celsius. Okay? So we'll have Q dot, which is going to be equal for all the cases. It's equal to, okay, for sure, minus kappa A dt dx. But then we're going to be able to say that it's equal to minus kappa from 1 to 2 times the area times the variation in temperature from 1 to 2 divided by the thickness from 1 to 2, which is also equal to minus kappa from 2 to 3 times the area times temperature difference between 2 and 3, distance between 2 and 3, which is also equal to between 3 and 4. So realizing that these are this heat flow is the same for each for each section is actually the key key reasoning, right? Starting from there, we're going to see that things get a bit well, simpler. Yeah, it's just math at this point. Okay, so one okay, so one thing we can do is to put the constant things on one side. So we're going to say that Q no, actually what we want to do is isolate the temperature gradients. That's the thing that we don't know yet. So we can say delta T12 is equal to, so it's going to be Q dot over A times delta X12 over A over kappa 12, and there's a minus somewhere, right? You agree with this? Okay, let me write it immediately as T2 minus T1. And then we also have T3 minus T2 is minus Q dot over A times delta X 23 over kappa 23, and we have 2 T4 minus T3 4, and then again this Okay. What can we do with these three equations? I'm sorry? Yeah.
Solve for T23.
Yeah, we can solve for T2 and T3, or we can also say, actually, I don't really care about T2 and T3, and we can try to eliminate T2 and T3. And in this formulation, there's a very simple way of getting rid of T2 and T3. You add them all, right? So you have you can start from here. T4 minus T3. If you add this, you're going to get T4 minus T3 plus T3. They're going to disappear, but there's going to be a minus T2. And if you add this one, then these are going to cancel, and you're going to end up with T4 minus T1, which is something that we know.
Cool, no? So we add them, plus, and then we get T4 minus T1, and on the other side, we get minus Q dot over A times the sum of these things. Okay, I'm going to call them R12 plus R23 plus R34. Okay, and we're going to define this. Thickness over thermal conductivity is called thermal resistance.
So maybe you see the analogy with yeah, question?
Why is the area constant?
Because we assume that the window is, it's one square meter, so the heat is going through this area all through, right? I mean, there's the same area through which heat is going in air and so on, right? So this area is the same throughout. So do you see the analogy with an electric system, right? It's like putting resistors in series, and when you put resistors in series, you can add them together. And really, the resistors is a reciprocal of conductivity, so there's a real connection between the two. In some cases, if you look up tables again on the web, if you want to know, for instance, if your house is well isolated, in some cases that's a thermal resistivity that are going to be given, thermal resistance, and then of course what's in there is already the thickness of the material. So it's so they're going to say, a brick wall has this thermal resistance, but of course if you put twice the thickness of this brick wall, well, you double the thermal resistance. Yeah.
So now we've got all the numbers, huh? We can put everything together. We can isolate Q dot. So it's A, divided by the total. There's a minus, yeah. Total resistance times T4 minus T1. And then if you put in the numbers, you're going to get 46 watts. Okay. So this air layer between the two glass panes is actually very, very, very useful. Yeah, which is not that surprising, is it? It's the same thing actually as bears that hibernate. They grow this fur layer that's roughly this thickness, and the point is that this fur traps air. So you have a 10 centimeter layer of air that is fixed, right? It cannot flow. If it flows, it doesn't work. But if it's trapped, then it's a really good isolation, and that's how these bears can survive for many months. Just emitting just a tiny bit of heat, of course. Yeah.
Do you mean T4 minus T1?
in the up duct below the addition.
Yes. There. Thanks. Yeah, I've seen a problem actually that I was thinking of maybe putting in the next problem set, but I don't know, where you model a bear as a sphere, like physicists like to do, and you can calculate how much heat is emitted. Okay, good. So now now you can use this Fourier's law for any kind of situation. I'll try to give you maybe one more exercise somewhere just to make sure that you guys know how to apply it in maybe a few different contexts. It might come up useful. Who knows? Wink, wink. Okay. Let's continue now. If we want to, then the next step is going to say, okay, I would like to know what is the heat conductivity, what is the thermal conductivity of an ideal gas, right? We're interested in ideal gases. We know how to deal with them. We know we have this little model of the colliding molecules, and then we're going to try to compute from first principles how is heat conducted by an ideal gas. And the first thing that we need before that is the concept of mean free path. Okay, so we're going to take a little detour through mean free path, which is a relatively simple concept, right? So we imagine, well, the new thing that we have to introduce is the fact that the particles actually have some diameter. Okay, so the molecules have some area that if there's there's another one is going to hit. Okay. For now, what we've done was always to assume that they're point-like. I mean, they collide, but we never really considered in more detail what it could mean to have that molecules actually have a size. So now we have to introduce some size. We're going to say that it's d, this diameter, and then there are others in a gas somewhere like this. Okay. And this one has some velocity vector, let's say in this direction, okay? And the idea is that we're going to ask how far can it travel before it's going to collide with another one. Yeah? And the construction we have to do is that, well, we have to kind of construct a cylinder around this, like this. And then what you're going to find is that a molecule that is, for instance, here is going to collide, right? Even though its center is out of the cylinder, they're going to touch each other. So you have to construct a cylinder that is actually twice the diameter of the particle, and any other particle whose center is within this radius is going to collide. Okay, so so the area here is pi times d squared, and not pi times r squared. Yeah, it's twice the diameter, which becomes the radius of the cylinder. Yeah, and this is often written as sigma, and it's called the cross section. Okay, cross section. If you go into particle physics, you're going to talk about cross sections all the time. Okay, and cross section is a way to quantify how likely it is that there's going to be a collision between two particles. And if you go in particle physics, pretty much that's the only thing you care about: colliding particles. Right? So I don't want to. I'm not saying this in a negative way, right? But it's yeah. Essentially, the whole physics. If you go down to the basics of what we know, everything that's happening is just colliding particles, really. Okay. So what is the volume swept over some time? That's the question we ask, right? Volume swept over time t. Well, it's this pi d squared times the velocity of this particle times the time t, right? And then we can ask what is the number of particles in this volume, or molecules. And it's just the number density times this volume, right? So what this means is that the time, in average, the time it takes to find one molecule in this volume, you know, how long do you need to extend this volume until there is an average one molecule in the volume? This is the time, this is the mean time between each collision. Yeah? So, what this means is that, okay, this guy is a little too far out, that we're going to call it tau. It's 1 over pi, not 4, but pi, n d squared v. And that's the average time between collision. It's almost true. Okay? We've forgotten one thing. That the other molecules are actually moving also, right? You could say, well, it doesn't really matter, the density is always the same, but actually it does matter, okay? And I'll tell you why. What we should put here instead, so what we should do is consider, you consider a pair of particles, and this particle could be going this way, say, and then you're going to say, okay, I'm going to go in the frame of reference where this one is not moving, okay? And then you have to consider the relative velocity of these two particles instead, okay? So this v should actually be a relative velocity. So need to use v relative instead of v for the molecule. And then you would say, okay, v relative in general, if you take a pair of particles, is equal to v1 minus v2, right? Or v2 minus v1. And then this means that v relative, not with t but with an l, squared, if you look at the expectation value of this, you're going to get the expectation value of v1 squared plus v2 squared minus 2v1 dot v2, right? They're vectorially subtracted, which means that when you square them, you do the dot product between the two, and there's going to be the cross term, which is a dot product between v1 and v2, and there are the two terms, which is v1 dot v1 and v2 dot v2. Okay? This, once you do the average, because they're all the possible directions are allowed, is going to disappear. But you're going to get these two there. So what you see is that, so this is 0, and then what you see is that you get expectation value of v1 squared plus expectation value of v2 squared, but of course, since they're taken both from the same distribution, all these particles follow Maxwell-Boltzmann distribution, this is equal to 2 velocity RMS squared. So what this means is that we have to replace v with 2 VRMS. Okay? No, v squared with 2 VRMS squared. So it means that the mean time between collisions is going to be 1 over square root of 2 times pi n d squared VRMS, and a mean free path, which is equal to, we're going to write it like this, if you multiply by VRMS, you get what's called a mean free path, and it's just 1 over square root of 2 pi d squared times n. Okay, so we've derived these two quantities.
Okay. So, what's interesting is that really it's pure geometry, right? We didn't talk about temperature, we didn't talk about pressure, or and really it depends only on the density, and it doesn't depend on anything else. Well, of course, it's the size of the molecules, but it doesn't depend on temperature. Are you surprised that a gas that is warmer, if you increase the temperature of a gas, the mean free path is going to be the same? Molecules are going faster, right? But really, if you think about it, it's just like accelerating the movie. It doesn't change anything in the geometry of things, right? There's the length of the path between collisions is going to be only determined by the geometry and not the thermodynamics. Yeah. Okay, so see you on Thursday. We're going to continue.